Hello everybody. Today we're going to be talking about triple integrals. Now, if you recall from last time, we were working with double integrals. And to work with double integrals, we needed to do a few things. Number one, we needed to identify, do we want to work with double integrals in Cartesian coordinates, or do we want to work with them in polar coordinates? And it was only then that we could start trying to set up these integrals, that way we can evaluate them. It's going to be very, very similar working with triple integrals. So before we get into it, I want to go ahead and I want to actually give the definition for the triple integral that we are going to be working with over a box. After we do that, we're going to go over a bounded region, and then we'll just keep on elaborating from there. Alright, so here's the definition that we're going to be using for triple integrals for a function f over the box B. That definition here is given by this triple integral, and it's going to identify some random sample points within this boxed region. And when we start looking at this, we want to make sure that any one of these regions that we find, or any one of these values that we observe, can be looked at as some x, some y, and some z coordinates because we're looking at the region that's a box. So when we choose a random sample point, the random sample point can be inside of this region, and what we then want to do with that region is we then want to create a random box around that region, and that's what this definition then says, that if we can accumulate an infinite amount of those boxes, then we'll be able to approximate the volume here, at least for the area that we're integrating, or for the region that we're integrating. All right. Now, if we're working with box regions, all right, that's more of a rectangular region as you're looking at it for domain, but in 3 dimensions, in R space 3, that's a boxed region. Then what we want to do is we want to use what is known as Fubini's theorem. Fubini's theorem is going to allow us to be able to change limits of integration, or differentials along with their limits of integration to our choosing. All right, so I'm going to write on here Fubini's theorem really quickly, and then we'll get to see how we're going to use Fubini's theorem. All right, so let me get that here. There we are. All right, let's make that go away. There we go. So here we go, Fubini's theorem. Now, Fubini's theorem is going to tell us that if we have, if we have a triple integral, say that we're working with a to b, c to d, and then e to f, there we go. And we have some function in here, f of x, y, z, and this is going to be dx, dy, then dz. Then Fubini's theorem, because this region is going to be over a boxed region, we can write it as this integral, a to b, the integral from c to d of f of x, y, z is equal to, and then the first innermost integral, the first innermost iterated integral was c to d, and that was the differential dy, so dy must come first, then the next limits of integration reference our dx, and then the last limit of integration references our dz. And we can keep on going with different representations here. So we're not just limited to saying these are the only 2 limits of integration or the 2 setups that will work. We can actually keep setting different ones up. All right, so there's actually a number of them that we could set up that we would still be able to evaluate this integral for, and it would still be an easy time. So Fubini's theorem, this only applies to box regions. And again, we got to be careful with that, because as you saw back in polar coordinates with double integrals, we can't exactly use, or we don't exactly get rectangular regions every single time that we set this up. So Fubini's theorem is very nice in the sense that if we can use it, great. If not, well, we have to find a different way to evaluate. So let's look at this example. We want to evaluate this integral. It's a triple integral over a boxed region for 4x squared y minus z cubed dv. Now I want you to pay attention to the notation here. We do the triple integral, and then we do a sub here, which is the notation for the region. If it's b, it just means we're integrating over a boxed region. dv, this is a differential with respect to some volume that we're going to be looking at. And so this is going to be where the boxed region is given by 2, 3 cross negative 1, 4 cross 1, 0, 0, 1. There we are. So what this notation then says, it's going to give us that this here is our x interval, this here is our y interval, and this here is our z interval. Which again, if they're giving us intervals, that means we're just creating this rectangular box region that we're going to be integrating over. So by analyzing this problem, we're free to choose whichever innermost integral we want to set up. We could set it up with dx first, with dy, or with dz if we choose. All right, so in the interest of things here, using Fubini's theorem, I'm going to say that my triple integral over this boxed region that I have for 4x squared z minus, 4x squared y minus z cubed dv is going to be equal to, and I'm going to leave the spacing on the integrals, that way I can write the limits of integration. Let's say I want to do z's first. I want to go from 0 to 1, and then I want to do x's, then I'll go 2 to 3, and then I'll do y's at the very end, negative 1 to 4. Again, these are in no particular order. I'm just using Fubini's theorem to illustrate that we will be able to set this up however we please without any fear of that we did it wrong. So since the innermost integral is from 0 to 1, that matches with the z interval, so that means this must be my dz. Second integral matches with my x's, so that's my dx. And then the third integral is my y's, so that's going to be dy. And the way we approach these triple integrals is the same way that we approached double integrals. We're going to do the iterated integral, the innermost iterated integral first. All right, so we're going to go through and we're going to evaluate this, or we're going to integrate this. So negative 1 to 4, and then 2 to 3. The innermost integral is integrating with respect to z. That means that this first term, 4x squared y, is a constant. So when I integrate a constant with respect to z, I must get a z in return, like such, minus the integral of this term. Well, that's just 1/4 z to the 4th. This is going to be evaluated from 0 to 1, and that's dx dy. Now, working with that evaluation, let's see here, I'm going to sub these into the z values. So 1 into the z value, 1 into this z value, and then 0 and 0. The zeros will cancel out, and so we're only left with 4x squared y minus 1/4, and that's it. because again, we inserted the 1 into the z values. So the z here just gives us this, the 1 here just gives us this, and then the zeros, again, like we said, they cancel out. So now we're just left with this integral here, where we have dx dy. So let's go through and let's evaluate this integral. Alright, so this is the integral from -1 to 4, and then I'm doing this with respect to x. So that means this is going to be 4/3 x cubed y minus 1/4 x. This is going to be evaluated from 2 to 3, and then we're going to do this dy. So let's go through now. This is going to be from -1 to 4, and I'm going to make my substitutions in here. So that's going to be 4/3, and remember, I integrated with respect to x, so we only evaluate the x values. Everything else was a constant, so we treat it as a constant. There we are. And then we're going to subtract 4/3 times 2 cubed y. Let's make that cubed a little bit better. There we go. 2 cubed y minus, actually that's a plus. That's going to be 1/4 multiplied by 2. There we are. And then we have dy. So it's going to be from -1 to 4. Alright, so the first term, that's going to be 3 cubed, so that's just going to be 9 times 4, so that should be 36y minus 3/4. This one here, that's 2 cubed. 2 cubed is going to be 8, so that's going to be 8 times 4, that's going to be 32, so that's 32 divided by 3, and that's a y. And then we get plus 1/2 here, and that's all dy. And what I want to do is I want to combine like terms before I integrate, just to make things a little bit easier. So I have this 36, and then I have minus 32 divided by 3. So that should give me a 76/3y. And then I have this 1/2. And then I have minus 3/4, so that should get me -1/4. There we are. Perfect. And this is all dy. So finally, all we have to do is just integrate this. So let's go ahead and let's integrate. That's going to be, let's see, that's going to be y to the power of 2. That means we divide by 2. So that's going to be 76 divided by 6, and that's going to be 38/3 minus 1/4 y, and that's going to be evaluated from -1 to 4. So we do 38/3 multiplied by 4 squared minus 1/4 times 4 minus 38/3 times -1 squared plus 1/4 times -1. There we are. Alright, so let's go through. I'm going to go to my calculator and see what I get here, because these two are going to give us some really large number. So I got 38, I'm going to multiply that by 16, and I'm going to divide that by 3. So for the first one I get 608 divided by 3. So this is 608 divided by 3. This next one I get -1, and this one I get -1, or sorry, -1/4. And on this one I get -38/3. Perfect. So I'm going to merge all this together. 608 divided by 3 minus 38 divided by 3. That gives me 190. So 190 minus 1 gets me 189, then minus 1/4. And that should get me 755/4. And there we have it. Alright, so not too bad. We get 755 divided by 4 for this integral. And again, what we did is we used Fubini's theorem to make sure that we can set this up. So as long as we're given some boxed region, and again, this was that boxed region, we can use Fubini's theorem. All right. Now, what if the region wasn't a boxed region? Then what? Well, we have a definition for these triple integrals over those regions that are not boxed regions. So here's a definition that we use for these triple integrals over bounded regions that are given by E. So again, these bounded regions, they could be anything that we'd like them to be. All right, so long as they're just bounded regions in 3 dimensions. All right, so in other words, they create a volume, and that's why we have this dv that we want to differentiate with respect to, or that we want to integrate with respect to. All right, so this is a way that we work with the notation. Now, if at any point in time we are asked to find the volume, and strictly the volume, over any bounded region, then all we do is set up a triple integral over that bounded region, and we would find that volume. All right, so there are small subtle differences between this formula here, the triple integral over general regions, and the volume to find a, the formula to find a volume using triple integrals. All right, so again, just subtle differences that we work with. So let's look at these triple integrals and see what we can do here. So in this example, we want to evaluate, the double integral over this region for 2x dv, where E is a region under the plane, and this is going to be 2x plus 3y plus z is equal to 6, that lies in the first octant. All right, so what we want to try to do is we want to try to envision what's happening here. All right, we want to envision this shape that we're trying to look at. All right, so I'm going to give you a really quick depiction of what this shape should try to be looking at. All right, and I'm going to draw this using just my ruler. So I'm going to get a coordinate system going really quick, the x, the y, and the z, and then we'll get to drawing that figure out. All right, so here's my x, y, and z coordinate system. Now, again, I want to be in the first octant. All right, so the first octant is going to be where all of the values are positive. And now I want to graph this plane right here. Now, the easiest or the best way to graph the plane is to interpret the intercepts. So when does the plane cross the x-axis? Well, we would make y and z both 0. So making both of these 0 would give us 2x is equal to 6, which would mean that x is equal to 3. So at x is equal to 3, we have 1 here. All right, that was 3. And then to find out where it crosses the y-axis, we set both of these x's and z's to 0, and we get that y is 2. So there we are. And then the very last one is when z is equal to 6, that's when x and y are both 0. So that's going to be somewhere up here. Now, when we draw this, we're just going to say, hey, we're looking at this here. Here we are. There we are. So we're looking at this pyramid thing, this pyramid object, and that's the volume that we want to integrate over. So we're not finding the volume, but again, we're finding the, we're integrating over that volume. So now that we have a depiction of this, we can now go through and try to set up our integral. All right. So the first thing that we're going to want to do after we try to visualize this, and again, if you're having trouble visualizing this, you can just go on GeoGebra, type in the equation of the plane, and you'll be able to see that intersection, hopefully automatically. Now, typically on exams we don't have GeoGebra or anything like that available to us. So what we typically do then is we want to envision the domain. So what I want to do here is I want to draw the domain. Or let's sketch the domain. So I'm going to say sketch. Sketch the domain. And I'm going to put domain in quotations because it's the domain that we're focusing on right now, not necessarily the domain of the actual function that we're looking at. So let's go ahead and let's try to sketch this out. So I'm going to get a, let's see, I want kind of a good grid going here. That way we can see and we can establish what it is that we're going to be dissecting, or what it is that we're going to be looking for. Now, since this is all in the first quadrant, again, I'm only drawing this with respect to the first quadrant. There we are. So this is going to be y, and this is going to be x. So under these assumptions, I'm working with 2x plus 3y plus z is equal to 6. And now I want a projection. I want the projection only using these two values, x's and y's. Which means what I'm going to do is I'm going to consider z to be 0. In other words, that's going to take this x and y and z plane over here on the right hand side, and it's going to completely cut down on the z plane to only give me the projection on the x and y axis. In other words, I'm taking the projection of the surface onto the domain that I'm choosing. So doing this, if z is equal to 0, then we naturally get 2x plus 3y is equal to 6. And this equation I can go ahead and I can graph, right? I need 2 points, which means I need x's and y's, but I already have those x's and y's according to this. X is going to be 3, so I'm going to go 1, 2, 3, and then the y values according to this is going to be 2. There we are. So I'm going to draw my line here. There we go. So there's the equation of my line. And this line, again, has equation 2x plus 3y is equal to 6. So this domain that I said that we wanted to sketch is this right here. That's the domain that we want to sketch. Now, identifying that we want to sketch this particular domain, then what I want to do is I want to start setting up that triple integral. All right. So when we want to set up this triple integral using this specific domain, then what I'm going to do is I'm going to start by setting up my dx's and my dy's. All right. So that's going to be the first step. So let's work with this. All right, let's go down here, and that's going to be the triple integral over the region for 2x dv. And I'm going to have a triple integral here. Now the innermost integral I'm not going to worry about yet, because the innermost integral I'm going to consider to be my dz. And you'll see why that dz will focus on this piece over here. But for now, let's work on this integral. So what I want to do is I want to take these vertical heights, taking those vertical heights first. The vertical heights here, they're going to go from 0 over to this line, and that's going to get me those vertical heights. Those vertical heights will always be changing with respect to y, which means I got to find y in this particular case. So let's go ahead and let's solve for y. Y in this particular case, let's see, we're going to have negative 2x plus 6 all divided by 3. Perfect. So in here, I'm going to have from 0, that was from 0, all the way to this function here, which is negative 2x plus 6 divided by 3. There we are. Pretty good. And then after these vertical heights, then I want to change these vertical heights for every single x value that is given. Therefore, as the x values change, the y values will automatically change with them, and that's what this calculates. So the x values that we're now looking at, and let me choose a different color for this, these are going to be the x values that we're looking for. So the x values are going to go from 0 to 3. Now the innermost integral, remember that was dy. Sorry, not innermost, the second middlemost integral, that was dy. And the last one is with respect to dx. There we go. Now, we want to interpret the innermost integral here. So the innermost integral, we then have to talk about, once we finish calculating all of this area in 2 dimensions, then we're going to take a height. The height is going to go from any initial point in this area. That initial point is then going to create some height here, and that is going to be our z values. So we need to see what height this is on that plane. Well, that's kind of good because I should have actually used blue here. You know what? It's okay. I'll keep it with green. That's actually good because the equation of the plane that we have is 2x plus 3y plus z is equal to 6, which means any function or any z value can be thought of as negative 2x minus 3y plus 6. And that's the height here given for these values, which means the heights, they will always go from the z value, where z is equal to 0, because that's the one that we had assumed initially, up to those values for z, which are negative 2x minus 3y plus 6. There we are. All we have to do now is we have to evaluate this integral. So let's go through it. Let's start evaluating. Now you're going to see here that we cannot use Fubini's theorem here. All right, I simplified this top fraction in red. And then I want to evaluate the middlemost integral with respect to z. So that's going to be 2x times z evaluated from 0 to negative 2x minus 3y plus 6. And then that's dy dx. All right, pretty good so far. Equals from 0 to 3. From 0 to negative 2/3 x plus 2. And then this is 2x multiplied by negative 2x minus 3y plus 6. And then the 0 will cancel that out, so we don't need it. It's dy dx. Go ahead and distribute. That's going to be negative 4x squared minus 6xy plus 12x. And that's dy dx. There we go. So now we could keep on going. So what I want you to do here is I want you to try it. Keep going. So I want you guys to keep going. If you want, go ahead and pause the video. Once you pause the video, I'll come back and I'll actually give you the answer. But for now, again, I want you to pause the video and see if you can evaluate this double integral. All right, so take some time and do that. All right, so you should have gotten the answer of 9. Perfect. So what we want to then see is what type of integrals can we work with when we're working with these triple integrals. Now, in this particular question, could I have chosen my domain to be x's and z's instead of x's and y? Sure, I could. Or could I have chosen my domain to be y and z instead of x and y? Again, that's a possibility. The fact is that choosing the domain to be x's and y's is just beneficial because we're accustomed to using x's and y's as a domain. In triple integrals, we are not necessarily limited to that domain. So that means that we can sketch all of these different outcomes, all of these different triple integrals with different domains. And we can evaluate them differently, but overall to get us the exact same answer. All right, so let's go ahead and let's give that a shot. Give me one quick second. All right, so here on screen now you have the different types of integrals that we can work with when we're working with a triple integral over some bounded region E. The first one, we typically call this a type 1 integral. A type 1 integral basically has the domain being x's and y's. And you're going to see that as I go through the remainder of the course, my first question with these types of problems is always, what do you want your domain to be? Do you want the domain to be x's and y's? Great, then that means we're setting a type 1 integral. And the reason I don't say type 1, type 2, and type 3 is because, again, when you go through different books or through different courses, you lose that terminology, that type 1, type 2, and type 3, and you go back to this particular integration or particular decision to identify what is that domain that you want. If you choose x's and y's, then that means the outermost 2 integrals are going to be a part of that domain. The innermost is the variable that you didn't choose. A type 2 integral has a domain of y's and z's. So the domain of y and z, again, we want to work with, hey, is the domain that we want to sketch in y and z? If it is, great, then the 2 outermost integrals are y and z. The innermost is the x values that we didn't choose. Type 3 integral. Type 3, we basically have the domain of x's and z's. So if we see the function that we want to integrate and we say, hey, I think we want it to be in the domain of x's and z's, perfect. Let's put that in the domain of x's and z's and see where that leads us into. All right. So within all of these given values, you're going to see here that given the first type of integral, if we set up the first type, then the 2 outermost are free to choose how we want to set them up. Is it going to be dx dy or is it going to be dy dx? In other words, this has not only one setup, this actually has 2 different setups. The first setup is dz, then dx dy, and then the other setup is dz, then dy dx, or vice versa, dx dy. All right, so second integral here, type 2, has another 2 different types. Type 3 has another 2 different types. Here we have a total of 6 different integrals for the integral over the region for some function of f of x, y, z with respect to dv. So we have 6 different integrals that will get us the exact same answer. All right, so we got to sit back and think about it for a bit, because that's a lot now, right? It's not just one straight integral that's going to work. It's actually going to be 6 different ones that work. And the first question that should always be stemming should be, what is the domain that we choose? All right, so with that being said, we now want to go through an example. So on this example, what I'm going to say is that we want to determine the volume of the region that lies behind the plane x plus y plus z is equal to 8, and in front of the region in the yz plane that is bounded by z is equal to 3/2 square root of y, and z is equal to 3/4 y. All right, so determine the volume of the region that lies behind that plane given by x, y, z is equal to 8, and in front of the region in the yz plane. All right, so we have some yz plane, all right, that is bounded by z is equal to 3/2 y, and z is equal to 3/4 y. So there's a question. Now, typically, if we were in class, I would then ask you all to determine what type of integral do we want to work with, or what type of domain do we want to work with? Do we want to work with the domain that is in the x and y coordinate system, the domain that is in the yz coordinates, or the domain that is in the xz coordinates? All right, now a quick hint to this is this part right here. We want this to be in front of the yz plane, which should be a natural instinct for us to say, well, maybe the domain that we want is going to be that domain that is yz. So I'm going to say here, choose a domain. In other words, I'm saying choose a choose a domain system that you want to use. For us, we're going to be using y and z plane. All right, so that's the domain that we want. So when we're setting this up, we're going to be looking at this type 2 integral. So a type 2 kind of setup, where we have the domain of the y and z plane. And again, the type doesn't really matter, it's just the domain that really matters here. So let's go through and let's sketch anything that we have within that domain. All right, so I'm going to get a grid going here for us. That way we can start sketching this function. All right, it looks like it might be in the first quadrant for this plane, which is good. Let's see here, where we are. Let's get that hidden. All right, so that's going to be y and z, so this is going to be z, and this here is going to be y. All right, nice. All right, so now I'm given some functions here, so I'm going to go through these functions here, and I'm going to see what these functions actually give me. All right, so I'm actually going to go with the first function. Let's do this in color purple. All right, so I'm going to choose z is equal to 3/4 y. So if z is equal to 3/4 y, this means that we have an intercept here at 0, 0. Slope is 3/4, so I go up 3 and then down to the right 4. All right, I'm going to kind of keep that in mind. The next item that I also want is z is equal to 3/2 square root of y. Now, if z is equal to 3/2 square root of y, again, we can start looking at this, and this is just a square root function, which does this, scaled by a factor of 1/2, so it's going to be a little bit thicker, a little bit more wider than normal, but we'll get there in just a bit. All right, so let's go through these 1, 2, 3, 4. Oops. And I actually want there we are. All right, so the first one we go up 3, 1, 2, 3. There we are, and then we go over to 4. Wow, my scale is way off. You know, it's okay. There we are. Draw the line there. Perfect. All right, so that is z is equal to 3/4 y. And then we're going to draw the other one, 3/2 y. So if y is 1, then we typically get 3/2. So y is 1, so it's going to get us 3/2. All right, in other words, 1.5. If y is 4, then we just get 3. So y is 4, we get 3. Here we are. So that function looks like that. There we are. All right. So it's looking pretty good here. So awesome. So now we got the YZ plane, that's great. So we got those bounded regions, that's awesome. So all I want to do at this point in time is I want to then start looking at how I'm going to set this up. Now the region that I'm going to be integrating over, or this domain that I chose, this domain is right in here. There we are. So when I'm trying to find the volume here, and I'm going to make sure I write this in red because they're asking me for a volume. So a volume here is just going to be the triple integral over some region, and we're just going to integrate over 1. All right. Now the z coordinate can come back just a little bit more, that way it can save me on room. There we are. So here goes the volume. The volume is that triple integral multiplied by 1 dv, and the innermost integral, again, I am not touching the innermost integral just yet. The innermost integral is that integral that we didn't touch, or that differential that we didn't touch. We didn't touch any x's, which means this is going to be dx, and we'll come back to what that's going to be. So let's focus on these integrals here. All right, we want the innermost. Typically what I like to do is I like to go for these vertical heights first. And so these vertical heights, typically this turns into like a Calc 1 problem, trying to identify these vertical heights. So these vertical heights are going to have a dz variable, or a change in the heights, which means it's going to be measured from the bottom of this red bar. The bottom of this red bar is given by this function, which is 3/4 y. The top of that red bar is given by this function, which is 3/2 square root of y. And all of those heights change whenever these horizontal heights change, or these horizontal values change, and that's our dy's. So our dy in this particular case is just going to go from 0 to 4. So they go from 0 to 4. Now, the ones that we didn't change, or the ones that we haven't focused on just yet, the x's. The x's, well, if we're going from the yz plane, would you then agree that yz plane, this here, would imply that x is equal to 0, which means x goes from 0 all the way to some top portion, or some top of the plane. Now, to get that equation of the plane, what we're going to do is we're going to use the equation of the plane that we're given to determine those heights. So x is just 8 minus y minus z. And that's 8 minus y minus z. There we are. So here's our triple integral that will find this volume. All right, so let's see if we can go through this. All right, from 0 to 4, then we're going to go from 3/4 y to 3/2 square root of y. Integrating this with respect to x is just going to get me an x, and then substituting in this value for that x just gets me 8 minus y minus z, and the rest of it's going to be dz dy. Perfect. So I want you to carry it from here. Can you finish the rest? All right. So I want you to keep going. So again, you can take some time, put pause on the video, carry out the calculations to see if you can get them. All right. Now, again, put pause on the video and I'll give you the answer as soon as you unpause it. As promised, here it is. There's your answer. 49 divided by 5. All right. So that's how we're tackling volume in this particular case. All right. Pretty good so far. All right. I like what we have going on so far. So what I want to do now then is I want to work with a different example. All right. To illustrate, again, the power of this choosing a domain. All right, so let's work on this example here, which says to evaluate this triple integral over this region for 3x squared plus 3z squared dv, where e is the solid bounded by y is equal to 2x squared plus 2z squared, and the plane y is equal to 8. Alright, so here we are. We have this question, and we're asked to find this evaluation for this triple integral. They give us the function, but they're telling us that e is going to be the solid that's going to be bounded by this particular function, and the plane y is equal to 8. Now again, the plane y is equal to 8, that's just a flat surface, but the equation that they're giving us has a very specific surface. All right, it has an actual name that we like to work with. All right, so when we're working with this, elliptic paraboloid, and that's this one here, this elliptic paraboloid is going to be cut off by y is equal to 8. So this elliptic paraboloid is opening towards the positive y values, all right, which means we kind of have a domain outline for us. All right, now the domain is kind of outlined for us in two different ways. The two different ways being that the function y is defined in x's and z's, and the function that we're integrating for is also incorporated with x's and z's. So choose a domain, and I'm going to choose the x and z plane as my domain. All right, so choosing this x and z plane, awesome. Now I kind of want to get a picture of what is happening here for this particular piece. All right, so I'm going to go ahead and I'm going to draw a quick sketch. All right, let me draw a grid really quick and I'll come back. All right, so here's your x, y, and z plane. Oops, excuse me. Wow, I didn't even realize I wrote this on there incorrectly until I looked up right now. So there we go, x, y's, and z's. Now what I want to do is I want to sketch this paraboloid really quick. So a quick sketch of this paraboloid will look something like this. Here we are. All right, and this paraboloid is going to be cut off at y is equal to 8. So when we get to y is equal to 8, it has like a cap on there. And so what we want to do is we want to integrate over this volume for this problem that we're given here. All right, so when I'm setting this up, when I'm setting up this triple integral, and again, I'm just going to rewrite this really quick, plus 3z squared. There we are, and this is going to be dv. What I want to do is I want to sketch this, or I want to integrate this over some domain, and that domain is going to be in the xz plane, but then my innermost integral that I want, the innermost integral is going to be with respect to the variable that I am not choosing. So the variable that we're not choosing for the domain is y's. So then in here, this is still going to be 3x squared plus 3z squared, and that was a square root. And I'm going to integrate this with respect to dy. Now, before we actually get into what this domain is out here, right, we said the first thing we wanted to do was choose that domain. That's great. Now that we chose that domain, again, we want to analyze the innermost integral. And I'm forgetting one thing. I'm forgetting the differentials over here. This is going to be with respect to some area because we took one of the variables out. It's not a volume anymore. Take one of the variables out and you're left with an area. So the y values. The y values here are changing. So what we want to do is we want to figure out how they're changing. All right, so let's figure out how they're changing. All right, if I take a y value, any one of these y values that exist in this paraboloid, I'm going to be choosing a y value here that will then give me the height that I'm looking for. So what height do those y values go through for each of these? Well, if you notice the bottom part, that's the paraboloid, but the top part, that's just 8. In other words, it's the plane. So my values, my y values, extend from 2x squared plus 2y squared all the way up to 8. And the reason I want to do this is because my domain kind of looks like it has a circular domain, does it not? Yeah, it kind of does. So because it kind of has this circular domain, I want to just evaluate this innermost integral first. And evaluating this innermost integral first is going to kind of lead me into what I probably should be using to evaluate my double integral on the outside. All right, and this goes from 8, or from 2x squared plus 2z squared all the way to 8, and that's going to be just dA. All right, so let's keep working with this and see what we get here. All right, so let's see, that's still a double integral over some domain that we chose, and this is going to be 8 multiplied by this function, that's 3x squared plus 3z squared. All right, and that's going to be minus that y value, which is 2x squared plus 2z squared multiplied by the square root of 3x squared plus 3z squared. There we are, and this is all dA. Perfect. Now, remember that domain. That domain that we chose that domain that we chose was x's and z's. So let's go ahead and let's start viewing that domain to see if we can start seeing what's happening here. All right, so I'm going to draw a quick sketch for this domain. That way we can analyze it and we can work with it just a little bit more. All right, here's 90 degrees, perfect. So let's get a 0. All right. Whoops. And there we are. Perfect. All right, so remember your domain, or the domain that we chose, technical difficulties here, wow, here we go. All right, the domain that we chose initially was a xz plane, so this is a x and this is z. Now, I want to make sure that I look at this equation in x and z plane. So when y is equal to 8, I want to see what's happening there. So I'm going to say y is equal to 8 and y is equal to 2x squared plus 2z squared. So setting both of these equal to one another, we see something occur. What is it that occurs? Well, we see this occurring. We get a circle centered at 0, 0 with a radius of 2. And this, ladies and gentlemen, is what we are integrating over for this region with respect to dA. So this is this domain D that I'm trying to analyze. All right, that's my domain D, and we want to analyze that domain. So within that domain, we can now start moving through polar coordinates. All right, so I'm going to say use polar coordinates for this double integral. So this turns into a question from early chapter 15, where now we want to tackle this using polar coordinates. All right, so if we're going to use polar coordinates here, that means my x's are going to be these r cosine thetas. So x's is r cosine theta, and z's here are going to be r sine theta. Nice. All right, so what that's going to give us now is the innermost integral is going to be the radii. All right, so let's go with the radii. The radii goes from 0 to 2. All right, radii goes from 0 to 2. The theta values, all right, theta values, they go from 0 to 2 pi. All right, so again, these were angles, and these in here were radii. All right, now my function cannot stay the same. So I need to make my inserts here. Well, x is just r cosine theta squared plus 3 times r sine theta squared. There we are. Minus 2 times r cosine theta squared plus 2 times r sine theta squared times the square root. Well, I'm running out of space here. It's okay. There we are. Let's see. There we are. Times the square root of the same thing. So that's 3 times r cosine theta squared plus 3 times r sine theta squared. Nice. And then I need my constants of integration. Constants of integration in this particular case is going to be r dr d theta. Now remember back to double integrals, that was just our constant of integration. By the end of this chapter, we'll explain where that comes from a little bit more in detail. All right. So once we have this, we can actually simplify it. Now, I know it looks a little bit intimidating as it is right now, but trust me, when we simplify, it makes things a little bit easier working with polar coordinates. Simply because this piece right in here, look at this. We get r squared cosine squared, and we get r squared sine squared. If we factor out a 3 and an r squared, then naturally we're going to be left with cosine squared and sine squared, which is just going to be 1. All right, so in this particular case, we get 8 times root 3 times r. And that's for this, because the square root of r squared is just going to give us r. Minus these values right in here. So those values right in there, well, that's just 2r squared multiplied by cosine theta plus sine theta, and that's just going to be 1, so that's awesome. And then in here, again, we're left with a root 3 times r because of r squareds. All right, that's those guys, and then we're left with r dr d theta. Nice. Now, let's see, from 0 to 2 pi, and then from 0 to 2, and let's go ahead and let's distribute those r values. All right, I see a constant of root 3, so I think I can factor out a root 3, and it'll look kind of nice. All right, so let's go through it. Root 3, and that's going to be leaving us with 8 r squared minus, that's going to be 2, let's see what else I have in here, r squared, r, so that's going to be r to the 4th. There we are. Perfect. And then this is just dr d theta. Nice. So as we see here, we have this really nice integral that we can go ahead and evaluate. Now, going through the evaluation here shouldn't take too long. All right, now I would encourage you all to keep going on this evaluation. All right, keep going. Now, the reason I say keep going is because I want you all to practice this integration. Yes, the setting up can be a little bit tough, but again, the setting up is the part that I want to look at, and the part that you need a little bit more work on is that evaluation of the integrals. That way you can pick up a lot of speed. All right, so put pause on the video, try to evaluate it, see if you can get an answer, and I'll post up the answer in just a bit. All right, and here it is. Did you all get the answer? I hope so. All right, so we got this answer. Awesome. Now, what I want to do is I want to start setting up these integrals in, let's say, different manners. All right, so I want to take one of my first integrals and I want to then rewrite it in terms of different domains. All right, so let's go to that question that we want to observe. All right, so here's going to be the question. Express the integral for this dv as an iterated integral in 6 given ways where E is the solid bounded by the given surfaces. So we're going to have the surfaces given by, oops, why is this not working for me? Given by, there we go, x is equal to 2, y is equal to 2, z is equal to 0, and then we have x plus y minus 2z is equal to 2. Alright, so take some time, digest a question, write it down, and then we'll get started on it in just a little bit. And I'm also going to give you a visualization, so when we get started in a bit, I'll give you that representation of the surfaces and what it is that we're looking at. Alright, so back onto the multivariable GeoGebra course that I have set up for us. Once we go down here to this very last example, the one that says triple integral stuff, very hush-hush, I want to click on that one, and that one's actually going to be this example that I have given to you all previously. That says I want to start looking at this surface-wise. So I'm going to look at this surface-wise, and I'm going to say show the surfaces, and here's all of those surfaces. Alright, nice. So here I am looking at all of these surfaces. Wow, now trying to find an intersection of those surfaces is kind of tough. So what I did is I went through and I parameterized the intersection of those surfaces. There we are. And you can see it right in there. So if we start zooming in just a little bit more, you'll be able to see it. Now I want to go ahead and I want to hide the surfaces now, and this is that projection, or that surface that we're trying to integrate over, that volume. So there's the region. Alright, now let's try to do this now, try to use non-GeoGebra techniques. Alright, so now that we have a good visualization of what's happening and what it is that we're going to be integrating over, we're going to try to then mimic that on our own without drawing this in RSpace 3. So let's go back to the workshop. Alright, here we are. So what we want to do here is we want to then start picking a domain. What domain do we want? Well, again, we're going to have to go through all 6 domains. So because we have to go through all, sorry, not all 6, all 3 domains. And because we're going to have to go through all 3 domains, it doesn't matter which one we choose. So I'm going to say here, let's choose the X and Y domain. In other words, the X and Y plane. Alright, so if we're going to start working with the X and Y plane, that means that the 2 outermost integrals are going to be X's and Y's, and the innermost integral is going to be that Z value. Alright, so let's look at what this is going to be looking like. It looks like the triple integral over the region for this function f of x, y, z, and that's dv. And I'm going to choose some domain that I want, and again that's going to be the x and y plane, and the innermost integral is going to be some z values that we are going to focus on. That's going to be dz, and this is all with respect to dA. Alright, so let's go ahead and let's start drawing this. So let's go ahead and sketch the domain first. Again, anytime that you're working with these types of problems, you always want to go with the domain first. As soon as you can figure out what domain you want, what domain is it that you're going to focus on, everything else kind of just falls into play after that. Alright, so let's go here and let's go, there we are, that looks good. Let's hide that. Alright, so I chose the x and y plane. That means that's my y, and that means this is going to be my x. There we are. Alright, now I'm given a few values. I'm given x is equal to 2, so I'm going to take that x is equal to 2. Alright, so let's put some tick marks on here. So this is going to be 1, that's going to be 2, that's going to be 3, that's going to be 4. Alright, so x is equal to 2. We'll get that going for us. Here's x is equal to 2. Wow, that is horrible, horrible. Let's get my ruler out. There we go. So here's x is equal to 2. Nice. That was the first one given. Y is equal to 2. So let's get y is equal to 2 going here. That's 1. That's 2. That's 3. All right. Let's get my ruler here. I want y is equal to 2, and there we are. So there's y is equal to 2. And then finally, I want a different function as well. The different function here is going to give me from these two that I haven't used. So the two that I haven't used is z is equal to 0 and x plus y minus 2z is equal to 2. This is then going to tell me that x plus y minus 0, because minus 2 times 0, is going to be equal to 2. Now, graphing this function here shouldn't be too bad. All right, that I see as an intercept of 2 right up here, and it has a negative slope, so it's going to go down 1 over 1. All right, that's not bad. All right, let's get that going. Should be somewhere around a 45-degree angle, hopefully. Not quite, but it's okay. There we are. Perfect. So here is this equation. This is x plus y is equal to 2. Nice. So the region that we're looking at, this domain that I want to focus on, is this region right in here. This is that domain that I was initially talking about. All right. So now that I see that domain, I want to go ahead and I want to try to talk about these vertical heights. All right. Remember I said I always kind of want to do vertical heights to begin with. That way I can start extracting all the rest of the information from there. So these vertical heights, let's see what we have going on here. All right. So first integral for the outside region right here. So that's going to be these vertical heights. That means it goes from this equation, so the purple one, all the way to the orange one. The purple one has an equation of y is equal to, that's going to be 2 minus x. All right, and it's going to go all the way up to the equation of y is equal to 2. There we are. And then these vertical heights change whenever these x values change. And the x values only change from 0 to 2. The innermost integral now, I can then talk about. The innermost integral is going to be the z values. So we then need to see what z values are we going to go through. All right, so let's start looking at them, right? Is it going to go from this equation of the plane to z is equal to 0? Or is it going to go the other way around from this equation of the plane to 0? Now, the big question is, we cannot assume that it's going to go from 0 all the way to the plane. All right, we have to do some investigative work in order to determine that. All right, the investigative work comes from the domain. Look at your domain here. Looking at the domain, pick any value within that domain. Say that we pick, or you can actually pick anything on the boundaries as well. All right, so say that we pick this point, let's say 2, 2. When you substitute in the value of 2, 2, that means x is 2 and y is 2. Substitute it into this equation here. X is 2, y is 2. What do we get? X is 2, y is 2. That's going to be 4. Subtract it over. That's going to be 2 minus 4, which means z is equal to 2. What that tells us then, or sorry, z is equal to 1. My apologies. So what that's going to tell us then is that if z is equal to 1 when x and y are both 2, then that means that's higher than z is equal to 0, which means this must go from 0 all the way up to the plane given by the z-axis. So let's solve the plane for the z-axis. All right, I want to do that in, already chose green over here. Let's choose a different color. Let's choose light blue. So here what I'm going to have is that x plus y minus 2z is equal to 2, which means that z is going to equal to, that's going to be, oops, excuse me, that's going to be x plus y minus 2 all divided by 2. All right, so then that means these z values go from 0 all the way to x plus y minus 2 all divided by 2, and that's again for this function f of x, y, z, and that was dz, the innermost. The second innermost was at dy, and the last one was our dx. So here's one of our first answers. This is one of the first answers. Now, if I wanted to re-index this, again, choosing a different outermost integrals, the outermost integral then, I would then need not a vertical height, but I would now need a horizontal height. So look at this horizontal height here. This means that our x's are going to change first. So the x's in this particular case go from x is equal to 2 minus y all the way up to x is equal to 2. Which means the middle integral that we're looking at is going to go from 2 minus y all the way up to x is equal to 2. There we are. And those horizontal heights change for every y value, and those y values are changing between 0 to 2. Height-wise, z value-wise, that doesn't change. Because all we did was we reoriented the domain, has no effect on the heights for the actual function. Which means we changed dx and dy, so that dx comes first and then dy comes second. This is the second type of integral that we can set up. So as you've seen so far, that one integral, that one triple integral has two different representations so far. We need to work on a third different representation. And that means we now have to choose different domain. So let's choose a different domain. That was x and y. So let's choose a domain of, let's say, yz. So the y and z plane. All right. So if we're working with the y and z plane, then the triple integral f of x, y, z with respect to dv, I'm going to be looking at some region, some domain. Oops, excuse me here. This was E, and this is some domain. And then the innermost integral that I'm working on is the variable that I didn't choose, which is x. So this is going to be dx, and this is just going to be dA. So what I want to do at this point in time is I want to start analyzing that particular domain. I erased some of this stuff over here. My apologies. I am putting it back. There we are. All right, so let's start sketching that domain. That way we can start extracting what we're going to need. All right, so let's see if I can get x's and y's again. Or not x's and y's, but vertical. Here we go. All right, let's move that back. There we are. 0, and we're going to move it right up there. Let's move it right down there. Perfect. There we are. All right, it's looking pretty good. And this is the YZ plane, which means that's my Z values, and that's going to be my Y values. All right, looking pretty good. Let's get some tick marks going in here. So this is going to be 1, 2, 3, 4. There we are. All right, so let's start off with what we know. I don't see any x's, that's fine. I have y is equal to 2, so I'm going to graph y is equal to 2 really quickly. All right, so let's go with y is equal to 2. Whoa. Que pasa? All right, that's looking good. So that's y is equal to 2. Perfect. I also have z is equal to 0. So when z is equal to 0, that's going to get me this horizontal piece here. There we are. Oh, let's go back, go back. Ah, cheese and crackers. All right, here we go. So that's going to be z is equal to 0. So there we are. There's my z is equal to 0. And then I should have one more equation. And the last equation that I'm going to be looking for is the equations that I haven't used just yet. So the equations that we haven't used just yet is that x is equal to 2 and x plus y minus 2z is equal to 2. So if x is 2, this is going to be 2 plus y minus 2z is equal to 2, which means subtract this over and we get y minus 2z is equal to 0. All right, it's looking pretty good, which means this equation should give me that z is equal to 1/2 y. All right, that means we just have a slope of 1 over 2. That's going to go here. Let's get a ruler here. And let's go through. So there we are. Perfect. So now the domain that we're looking at is right in here. So that's my domain. Now, because that's my domain, I can now start talking about how I want to set this up. So, the innermost integral, again, is going to be the x values, and we'll talk about those x values. But what I want to do is I want to focus on my middlemost integral first. I typically always like to go with vertical heights first. So let's look at those vertical heights. Those vertical heights go from z is equal to 0. So that's going to be from z is equal to 0, and they go up to this green piece here. That green piece is just going to be, that case is z is equal to 1/2 y, so that's going to be 1/2 y. Perfect. All right. Now my y values. Y values are changing, and the y values are changing between 0 and 2. There we are. Now I need these z values. So the z values that I need, again, I'm just going to rewrite this really quickly. So that was dz and then dy. Perfect. My apologies. I said z values, but I meant x values. So these x values, so far we got that x is equal to 2, and we know that this plane can give us some sort of x value, so we need to figure out what comes first. Well, let's pick a value in the domain. Pick any value in the domain, and again, it could be a value that is on the border as well. All right, any value that you'd like. So you can pick, in this case, 1.5. So 1 and 1 comma 0.5, or you can just go with this value here or this value here. I want to go with 1, 1. Let's see what happens with 1, 1. What happens when z is equal to 1? Or, my apologies. It said 1, 1. Cheese and crackers. I meant 2, 1. So this means that this means that y is equal to 2, so that y is equal to 2 and z was equal to 1. All right, so if y is equal to 2, I'm going to put that into my equation. X plus 2 minus 2 times z, which is 1, is equal to 2. That's the equation of the plane that I have that I was given from the beginning. So 2 minus 2 gets a 0, which means x is equal to 2. All right, well, that didn't give us much. All right, so it gave us x is equal to 2, but we kind of already knew that because x is equal to 2 here. So let's pick a different value in the domain and see if we can then get something out. All right, so let's choose a different point. Let's choose this point here, which will be, what is that, 1, 0. All right, so 1, 0, so that means my y-coordinate is 1 and my z-coordinate is 0. So y-coordinate is 1 and z-coordinate is 0. There we are. So that's going to be that x is equal to 1. Nice. So what this tells me is that when I took that coordinate of 1, 0, which is a part of the domain, it gives me that x is equal to 1. That then tells me that the equation of the plane is actually lower than x is equal to 2. Which means we must be going from the equation of the plane up to x is equal to 2. So what does the equation of the plane look like when we solve for x? So the equation of the plane once we solve for x looks like 2 minus y plus 2z. There we are. And that is another one of our answers. If we wanted to rearrange this, again, we only work with the outermost integrals. The innermost iterated integral doesn't change because, again, the innermost integral didn't change with the height. So it still stays as dx, but now I want to change my dy and dz. Now, we cannot use Fubini's theorem because this is not a rectangular region, all right? So, working with this, we now need these horizontal heights. These horizontal heights now are going to be grabbed here. So I need these horizontal heights. So horizontal heights here, let's see, that's going to be the green part. That green part is going to go from the bottom of that green function. That green function was this one here. So what I need to do is I need to solve this for y. So solving this for y, this means that y is equal to 2z. So that's going to go from 2z up to y is equal to 2. So that's y is equal to 2. There we are. And then that means that these horizontal heights are going to change when the z values go between 0 and 1. And here's our different integral. Whoops. There we go. So here's our fourth integral. So far we have 1, 2, 3, and 4 integrals. What I want you all to do now is I want you all to try the next one, which will be the x and z plane that you're going to have to work with. So work with the x and z plane and see if you could draw the domain. Once you draw the domain, go through and set up those integrals. All right. Now, I'm going to leave it as such. And what I'm going to have you all do is I'm going to have you upload your answers onto the discussion board. So you're going to be able to upload your answers onto the discussion board with a picture or a PDF, whatever it may be, and we'll analyze them then. All right. So I hope you all enjoyed section 15.5, and I will see you for the next one.